Right. For the opportunity to make this presentation. I am Chathurangi Randiligama. I am a PhD student at QUT. The title of today's presentation is Detecting, Locating and Quantifying the Damages in Hyperbolic Cooling Towers using Vibration Data and Artificial Neural Network. Let's look at the content of today's presentation. This is the content. Let's talk about the background of my research. Cooling towers are high-rise reinforced concrete structures which is used to remove the waste heat from the water and transfer to the atmosphere through the process of evaporation. Therefore, these structures are subjected to large temperature variations. This, together with deterioration due to aging, environmental effects, and random actions, can cause de-stresses in these large structures. These de-stresses can go undetected as most part of the structure, especially its interior, is neither visible from the outside nor easily accessible, and the exterior of the cooling tower is also not easily accessible due to its height. Therefore, these distress can escalate and result in a catastrophic failure or collapses of these large structures. Their collapses can cause disruption to the power supply, and also it may cause expensive repairs. This slide captures some of the fast failures or collapses of cooling towers. As you can see, these are few locations and these are several reasons for those incidents. Cooling towers are vulnerable to deterioration of concrete and steel elements as shown in these two figures due to the extended exposure of heat, moisture condition with chlorides and carbon dioxide, and also due to the small concrete cover. Damage deterioration phenomenon can be categorized into three categories. First one is cracking. Cracking can be happen due to the thermal or moisture gradient, yielding of reinforcement. The second one is imperfection of geometry. It can be happen due to the errors in the initial construction, service load, and the operational conditions. And the third one is long-term deterioration. Therefore, failure or collapses of cooling towers can be happen due to the one or more combination of above effects. Therefore, all the structures around the world need to be monitored from time to time to check whether they are still safe to operate or capable of withstanding the environmental impacts. Damage can be categorized as any change in the physical property or a stiffness of the structure. There are two types of damage detection method. The first one is local damage detection techniques, and the second one is global damage detection techniques. Let's talk about the local damage detection techniques. Local damage detection methods are focused on non-destructive evaluation tools. They can be used to detect the damages in simple structures, and also they need a lot of time. They are very expensive, and they need prior localization of damage. Therefore, these local methods cannot be used to detect the damages in large or complicated structure like cooling tower. To overcome those limitations, global methods has been proposed. Global methods are focused on the vibration characteristic of a structure. Therefore, during this research, I have used the vibration-based damage detection techniques to detect the damages in cooling towers. Among these vibration-based methods, the mode-shape curvature-based method is mode-shape curvature is highly localized to the damaged region. Therefore, I have focused on that. The mode-shape curvature can be calculated from displacement mode shape by using central difference approximation as shown in equation number 1. Here, h is the length of the element, phi ji is the mode shape of jth element for ith mode, and the location of the damage can be found using the largest absolute difference of mode shape curvature between intact and damaged state, as shown in equation number 2. Here, the damage index di is based on absolute change in mode shape curvature. The highest peak in the absolute change in mode shape curvature along the path indicates the damage location. The proposed coupled method can be captured through the following steps. Preliminary studies indicate that the radial component of U1 and the vertical component of U3 consistently give the dominant contribution in damage detection. Therefore, first of all, I have extracted the effective mass of U1 and U3 direction of first three global modes considering the intact finite element model. After that, I have identified the maximum effective mass values considering these 6 values. After identifying that, then I have identified the dominant mode and mode shape component, which is corresponding to the maximum effective mass value. After identifying that, then I have extracted the mode shape data from the intact and damaged models using a one nodal path. And then I have calculated the mode shape curvature using this equation. And then I have calculated the largest absolute difference of mode shape curvature between damaged and intact state using this equation. Then I have plotted these damage index along that path, let's say in path AB. And the highest peak in the mode shape curvature along that path indicates the vertical damage location. Then we have to select the second vertical nodal path, either to the left or either the right of the current nodal path. Let's say if we select the one nodal path, then we can plot the absolute difference of mode shape curvature between intact and damaged state. And then we can compare the magnitude of the highest peak along the path compared to the previous plot. If it is decreased, then we can select the next vertical nodal path in the opposite direction. Then we can repeat this. Let's say if the magnitude of the highest peak along the path compared to the previous plot increase, then we can select the next vertical nodal path in the same direction. We have to repeat this procedure until find the highest peak among these nodal paths to locate the damage in horizontal cross-section. This is the proposed method. Carried out the experimental testing using a laboratory scale cooling tower structure as shown in this figure. In this case, we have used the single axis accelerometers. Therefore, single axis accelerometers were positioned using steel hollow cube as shown in this figure. And the random tapping was done using a vibrating hammer because these structures cannot excite naturally. Therefore, random tapping was done. And the data acquisition system was used to collect the acceleration data. And the LabVIEW-based data acquisition software was used to store the collected data and transfer to the PC for post-processing. And the data were transferred to the RTMS model analysis software to obtain the model parameters like mode shapes and the frequencies. Then I have validated the coupled method using experimental data under two damage conditions. The first one is damage at neck of the cooling tower, and the second one is damage at upper part of the cooling tower. In this case, first I have created the laboratory scale cooling tower using finite element software like Abacus. First I have created the intact model. Then I have extracted the effective mass of U1 and U3 component for the first three global modes. And then I have identified the dominant mode and mode shape component. In this case, it gives mode 2U1 component, and these are the test results for damage at neck. And these are the test results for damage at upper part. As you can see, line EF is very close to the damage location, which gives the highest peak. And the distance to the damage location for line CD and AB increase respectively. As you can see in the second one, the damage at neck, the damage at upper part, line GH is very close to the damage location. Therefore, these results demonstrate the feasibility of proposed method and the importance of identifying dominant mode and mode shape component in damage detection process. Then I have tested the coupled method using a real cooling tower structure. The height range from 80 to 240 meters. Considering three specific locations, damage at neck, upper part, and the lower part. And in this case also, first I have created the intact models, and then I have extracted the effective mass values of U1 and U3 component for the first three global modes for each structure. And then I have identified the dominant mode and mode shape component. Then I have used this dominant mode and mode shape component to detect the damages in these structures. This is for damage at neck, upper part, and the lower part of the cooling tower. As you can see, in all the cases, the proposed method is capable of identifying correct damage location. We tested this method using noise polluted data and limited number of sensors. The field testing conditions are simulated by adding white Gaussian noise. And these are the test results for damage at neck, lower part, and the upper part. As you can see, pink color line shows the damage indices calculated with noise, and the blue color shows the damage indices calculated without noise. As you can see, in all the cases, the proposed method is capable of identifying correct damage location even with the presence of noise. We have tested this method using multiple damage scenarios. As you can see, these are the test results. And in this case, these studies were carried out only for 2 damages in one nodal path. Let's say if there are simultaneous damage in 2 nodal paths, the more severe one can be detected first, and then we can fix it. And the subsequent monitoring can be used to pick up the remaining damages. Then I have tested the multiple damage detection with noise as well. And these are the test results. As you can see, in all the cases, the proposed method is capable of identifying correct damage location, even with the presence of noise. After completing the damage detection and location part, then I have moved to the damage quantification part. In this case, first of all, we have carried out the study of effect of damage location in predicting the damage severity. In this case, we have used the absolute change in mode shape curvature based damage indices for 20 different damage scenarios along one of the real cooling tower structure, considering 5 different damage severities. As you can see, the peak values of damage indices curves are different for 2 similar damage intensity at 2 different locations. These patterns can cause the problem when the location and the damage intensity are not known, because the absolute change in mode shape curvature based method by itself cannot quantify the damage. Therefore, I have introduced artificial neural network to overcome this issue. Let's talk about the artificial neural network. The mechanism of neural network inspires from the biological nerve system, as shown in this. The artificial neural network is a machine learning technique. It can predict the behavior pattern using set of data samples. The concept of neural network was introduced by McCullough and Pitts. As you can see, the structure of ANN is a combination of input layer, output layer, and the one or more hidden layers. As you can see, each layer has a number of processing units called neurons. In the study, I have used 612 data samples to train the network under the range of damage severities, as I shown in here. And the feed-forward neural network having one hidden layer with Bayesian algorithm is used to train the network. And also, in this case, I have used noise polluted mode shape data to train the network, considering the 5 different noise percentages. First of all, I have extracted the mode shape data from each and every model, and then I have converted it to the damage indices, and these damage indices were used as the input data for this network. And the severity and the location were used as the target values for this network. Once the network, after finding the best network configuration, few trials were carried out to acquire the best network with minimum error. After finding the best network configuration, then I have tested this method considering the different damage severity under different noise conditions. Here I have presented the few test results. As you can see, as shown in these graphs, the actual damage severity and the neural network prediction overlaps. Therefore, we can say that the proposed or the trained neural network is capable of identifying correct damage severity. And then I have done the same thing for multiple damage detection, multiple damage cases. I have trained and tested for a few test cases, as you can see. And in all the cases, the proposed or the trained neural network is capable of identifying correct damage severity for multiple damage cases. Okay, let's talk about the outcomes of my research. I have developed and applied a method based on vibration data and artificial neural network to detect, locate, and quantify the damages in hyperbolic cooling towers. And it enables the early detection of damage, retrofitting, and safe operation of cooling towers. These are my publications. And thank you for listening to my presentation.